Video help for problem 27.8. I want to actually clarify something about this, the beginning point, number one, and then I want to clarify the end point. In the middle, you'll find help with the calculation in our written homework advice. You know, when you write down a magnetic field and you say that it's linear, like we're always saying linear gradients, you have to remember that that by itself is impossible. You have to have something else to make sure the divergence of B is zero. That is, you'll see from a picture what I mean. You got to keep the flux, actually the flux in equal to flux out because there are no magnetic charges. So that really means you've got perpendicular components to your gradient that are just as big, just as important. Well, wait a minute. They're not just as important in the MRI because when we go to the rotating reference frame, this thing is sitting there constant, that we see it in the rotating reference frame. This thing we just zip past 1,000,000 times a second and it averages to zero. So we don't see the effect of this in the rotating reference frame, which allows us to understand why we ignore those components. But in doing this calculation and calculating the energy associated with a coil, we actually are including these components, and you'll see how. Well, I've got a gradient in the z, and remember this, that whenever we're talking about gx and gy, those are always the gradients in the z direction. We're always only interested in the z component of the gradient coil, or of anything. And in terms of the B0 and the gradient. And we've got to have, if I do have something linear in z here, I'm going to have something linear in rho, say, in an azimuthal symmetric thing in cylindrical coordinates. That is, I did my little divergence of B calculation here in cylindrical coordinates. And I do, my divergence is a little bit richer calculation. And I take this derivative and I take that derivative. And, this is not important for you to know in detail, but I'm hoping you understand it. I do my divergence in cylindrical coordinates, and I find out that I get for these two guys 2g rho plus gz, and that has to be 0. So g rho is a minus a half gz, and that corresponds very nicely to when you have something, a z gradient, then you've got a B field pointing this direction on this side and pointing the opposite direction there, which means you've got to have flux coming into this to account for the flux going out there. And that's why that extra term is there. And that's what we mean when we say B is kind of proportional to R, then you see it. Along Z, R is Z. Along rho, R is rho. And so just generically, B is growing like R, but we don't want it to be growing beyond DSV, as you'll see in a second. I'll say then that it's some constant times R, where that's the generic gradient strength, GZ. So you notice these gradients are related. So it's some generic gradient strength. I'll take this G0R. I do a spherical integration, and you can look at the written homework advice for that. And you get this very well-known result in the MRI circles about the energy dependence on R. Look at that equation 27-20 that, we reference in the problem statement. And the energy tracks inductance. Inductance we'd like to have as small as possible, but still have this good linear field in order that we can turn this coil on and off fast. Remember L, the bigger L is, the harder it is to turn it on and off. It has that decay time.